Well, good evening, everyone. Hope everybody's had a great day. My name is Mike Hogan. I'm going to be your guide for the next couple months, going through our TKT prep course, or telecommunication electronics, however you want to title it. I'm going to walk you through just walk you through the resources. And by the way, if you guys have had a chance to log in, if anyone has had a problem accessing the site, please let me know. If you tried to log in and couldn't get in, if you would let me know, and I'll get that straightened out as quick as possible. So is anybody having problems at this point? Have you tried to log in and had issues?
No, I haven't had problems.
Great.
Morning in
Well, if anyone has any issues, just let me know. If you hadn't tried to log in yet, that's okay too. Just try to log in as soon as you can, and let me know if you have any issues accessing the site. That's the Your Tech Training site. That's where all the resources are, and that's what I'm going to walk you through that as we start out today. First of all, just a little bit of background. I mentioned my name is Mike Hogan. I have been teaching electronics in the communications area, and really in the medical area for about 20 years at a couple different community colleges in North Carolina. And so it's a topic that I first was introduced to in the Marine Corps. And from there, like I said, picked up some teaching experience, and had a chance to work with CWA probably back about 2000. And then, just a chance to about a year ago, we started doing these TKT courses to help folks pass that technical knowledge test. And so they've been really successful to this point. And hopefully you guys will find that you're successful at the end of this course. As we go through the course, if there are ever any issues, any challenges, feel free to reach out to me. Just let me know what you're going through. Or if you're going to miss a class, if you'll let me know, I can make sure that if there's anything that we're going to record every session, but if there's anything that needs to be explained outside of the recording, I can certainly help you out there as well. Or if you're having problems with a topic, just let me know, and I'll be glad to connect with you, and we can do a individual session if there's one particular topic you need help with, or anything like that. Just, I'm here for you next couple months. You guys will have access to these resources well beyond the course. And so I know sometimes taking that TKT doesn't happen exactly at the end of this class. And so, you'll still have these resources to continue to study as you move into next year. So I want to walk you through the resources, give you an idea of what the course looks like. And we'll talk a little bit about the calendar and the way we're going to kind of run the classes, and then we'll dive right into the material. So let me see if I can share what the course is going to look like, the resources.
Hey, sir, there's a whole bunch of practice quizzes on those. Is that for, is that just for practice, or is that for submission?
So, when you mention practice quizzes, so there's some practice problems that are in the resources that we have, and everything, and this is probably the best way to answer your question. Everything that we have out there is for you to practice and to develop the skills. And so it's not a quiz for you to take and turn in for a grade. Everything here is, even the tests that we have, they're really a opportunity for you to kind of do a technical knowledge test, just to go in and kind of say, okay, do I really understand if it's series circuits, do I understand series circuits? You take that test. If you do well, great. If you don't do well, you take it again, right?
All right, thanks.
You're welcome. All right, so let's see. You guys see my screen? Basic Electronics course 110321.
Yes, sir, we do.
Yes. Yes.
All right, great. Sometimes I'll share the screen, and for some reason or another, it just doesn't happen. So, I'll usually ask you when I try to share a screen, just to make sure that you're seeing what I want you to see. That way I don't run off and get 4 slides in and then say, oh, we're not even looking at the same thing. So here we are, basic electronics. This course, the way it's laid out, you've got some sections up at the top. Now yours will look slightly different because I've got a few different options here that I'm looking at. But basically, when you log in, you're going to see some handouts at the front, schematic symbols, kind of step by step. Those things, we're going to go back and at some point pull them into a session. And so we may be talking about schematic symbols, and then I'll pull that up and I'll refer to it. But right now it's just there. We really put it up front because we wanted to make it easy for you guys to access at any time. What we're going to do day by day, so we'll have 12 sessions that we'll go through. And so we'll start session 1 tonight, and we'll just walk through these sessions. And you usually have a couple different resources. One, you've got video resources. And so you could actually select this video scientific notation, and it will show you a video of a previous class that we've taped. All right. And so that's you would be able to select that link and get pretty much what we're going to cover tonight, but it would be a different class, probably a different instructor. And so you got those video resources out there. If you miss a class, certainly that's a great opportunity to go back and, okay, let me watch a previous class. If sometimes it helps to have some information explained in a different way, and teachers all have their different ways to explain things. And so there may be a situation where I explain something and you think, well, I just don't quite get what he's saying. You might be able to go into this video resource, pick it up, and watch it, and it might be explained in a slightly different manner. And between the two, it might help you with your understanding. But those video resources are there. We're also recording all of our classes, and so we will have those available as well. So you could go back and watch the class. If there was something in particular that you wanted to go back and review, maybe a particular question was asked and answered, you could go back and listen to that answer again if you wanted to. We also have for each area, we've got PowerPoint that we will go through. These PowerPoint slides. I try not to read just off the slide. What we're going to do is we're going to put the information up. Some of them are wordy. They break a lot of PowerPoint rules in terms of the amount of words on a slide. But we won't just be reading PowerPoint slides, but they're there for you if you wanted to go back and review. Sometimes once you get the slide, that's enough to get you started and you remember what we talked about on each one of those slides. But we're going to go through these PowerPoint presentations each session. And then the other resource, the other two resources really, one is YouTube. We've curated some videos over this past year, what we thought was pretty good. And once again, it's an opportunity for you to hear from a different instructor, maybe explained a slightly different way about a topic. And so during the class, we'll go through a PowerPoint presentation, and then we may pull up a YouTube video just to watch the video and kind of rehash a little bit of what we've covered so that everybody's got a better understanding. We won't watch all the YouTube videos that are laid out in the course. Some of them Some are lengthy. Typically we won't watch very long YouTube videos. And then some of them, they do a good job of explaining, but I don't know that they necessarily bring anything else to the class at the particular time. And so a lot of times we'll skip right over the YouTube, but you can go back and watch those on your own. And then we've got these quizzes, and these quizzes, once again, they are a learning tool. This is not a grading tool. This is not for me to figure out, what grade to give you at the end of this course. This is strictly for you. And so without hesitation, you should go in and take those quizzes. They're set up so that you can retake them as many times as you want, so that you feel comfortable that you know the information. And so we're going to have those. Go ahead.
Are those questions the ones that will be asked on the TKT exam?
So I can't say that those questions are TKT questions. I can't say that. But what I can say is that those quizzes have been developed, and the handout that's in the section above. So if I go back up here, and okay, those are just practice problems. They must be down in a session now. But there are some TKT practice tests. Those tests and the quiz questions are developed based on feedback that we've received over the year. And so while I can't say that, yes, those are TKT questions, I'll say they're very similar. I'll also share that we are going to cover more information than is on the TKT. I've had students come back, folks come back who've taken the TKT and they've had questions in a couple areas, and then there's a couple areas they did not have questions on. However, in order for you to have a solid foundation, there's just some information that we need to cover. And so a great example is when we get into circuits and we're looking at different components and we're talking about resistors and resistor color code. We're going to examine the resistor color code and determine, be able to read that color code and tell what a value of a resistor should be. However, I've had several people come back and say, I didn't get any questions on resistor color code. So it's one of those things that we're going to cover just so you have a better foundation. So if you're working with circuits and you've got resistors, it's something that but it's likely that it's not going to be on the TKT. So the flip side of that is I feel very comfortable saying that every thing that you'll be tested on in terms of the TKT we'll cover in this course. And so you should have a pretty solid preparation for the TKT once you finish this course. Any other questions? Thank you for that. And when you have a question, absolutely jump right in. Don't feel like you got to wait for me to finish. This is a give and take. This is not as a formal as some classes that you may have had in the past. And so this is going to be a give and take. If you've got a question, bring it up. If you've got something that you think adds to the topic, bring it up. And you don't feel like you have to wait until we get to the end of the session or something like that, or wait for me to call on you. Feel free to jump right in. The other thing is there are times when we get noise in the background. I may have somebody walk up as I'm teaching, or you may have a kid or a wife or a husband or somebody that comes up and they're in the room and they're talking to you, or you may just forget that you're not muted. And if some of that happens, then I will mute you, just so not trying to be ugly about it, just so everybody else doesn't pick up on the conversation of what may be taking place in your environment. So just be aware of that. You're unmuted and then you start talking and we don't respond, I may have muted you for background noise purposes. So just be aware. So we're going to go through these sessions. Like I said, there's going to be 12 sessions. So as we scroll down, you can see that each one of these sessions can be pretty full. Now, we're not necessarily tied to covering all of that every session. In other words, if, for example, tonight, we didn't get to where I'd hoped to get at the end of this session, that's not a problem. We'll always go back and pick it up. We won't miss any information. We won't miss any material. If we've got questions or if we need to dive a little bit deeper to make sure we have an understanding, I'd rather do that than just cover the material so that we could say we covered the material. So, we'll go through each one of these sessions. There's the materials divided into 12 different sessions, and our class, as we, obviously we're here, so we figured out is Monday, Wednesday, and it's 7 p.m. Central. Now, we do have the possibility of getting into some holiday schedules. I think right now, unless I start seeing or hearing about some challenges as we approach holidays, I think we'll just continue Monday, Wednesday, and we'll just hit every Monday, Wednesday, unless I start getting some feedback that we're going to have quite a few folks missing. And if we do, then I'll start making some arrangements. But otherwise, let's just plan on Monday, Wednesday, every Monday, Wednesday for the next 6 weeks. Any questions so far?
I had a question.
Sure.
I took the TKT a while back, and it asked about computers.
Yes.
But I didn't see anything about it on the thing.
So when we get down to toward the end, let me get session here.
Yeah, because it was like old computers too. So like
when we get to session 9, we're talking about data communications. 10, we're talking about basics of computer, and so we'll get into the different components and the different pieces of a computer. We'll look at some outdated pieces and some updated pieces, and then we'll go ahead. We're gonna talk about some numbering systems. Binary will be one of those. We'll talk about hex. We'll even talk about octal, even though I've not had anybody that has come back and said that octal was on their TKT. Going back to computers, you can see when we get down to those last few sessions, we're into computers and networking, talking about operating systems, and then also talking about network troubleshooting. And so, yeah, I feel comfortable that we will hit those areas that are tested on the TKT. Now, when we get to those sections, and if you've taken the TKT before, please provide input and ask those questions that are aligned to what you saw on the TKT. It's only going to help everyone, right? And so we get to the computer section, and you remember questions on things that we're not covering, let me know. And if it's not in the course, then we'll add it to the course. We'll figure out what is missing, and we'll make sure you get it. All right. Any other questions? So I didn't hear that. That was broke up a little bit. Okay, I'm having trouble picking that up. I'm not sure what that question was. Could anybody hear that? Okay.
No, we couldn't hear it.
So in terms of tools for Zoom, obviously we've got the video, audio, and in terms of video and audio, I'll leave it up to you guys. If you want to turn the video on, feel free. If you would rather leave the video off, that's perfectly fine. Typically what I'll do is I'll have my video on, unless there may be a odd time where if I start having any bandwidth issues, then I'll start scaling back and I'll cut the video off. And so you guys, you do whatever makes you feel comfortable. And
you see that fiber where you're at? So you won't have balance issues.
Absolutely. Absolutely. All right. And in terms of what I was going to say, tools, and I see somebody's used it. So let me go. All right. So if you, and Michael mentioned chat as well. Yeah. If you can't talk, for some reason, if we can't hear you, feel free to use the chat box. And now you guys will have to help me monitor that. So if you see a chat that comes out, somebody asks a question, then I don't, I'm not necessarily watching the chat. So if somebody could, if you see something that I haven't addressed, feel free to bring my attention to it. All right. If there's no other questions, let's go ahead and dive in.
I got a question for you.
Okay, go ahead.
I'm logged in off my phone off Zoom, but my son can't log in, so I'm trying to share my phone with him, and it's not letting him log in off his Zoom, but he's able to log in off of I guess on that UTech training. He's able to get on that UTech training, but he can't get on the Zoom call off his phone.
Okay. Does he have the correct meeting information?
Yes, sir. It says, please wait for the host to start this meeting. That's what it says.
All right, let me see if I can, hold on one sec. Let me stop that for a sec.
Losing my it's on the computer.
Are you on?
Not on. That's what it says.
Okay.
Oh, yeah.
So I thought you might be in the waiting room, but I don't see anybody.
Try it off your phone. See if you can get on with your phone. He tried it off his laptop and his phone, and it just says, please wait for the host to start the meeting. You want me to exit and have him go back in?
Yeah, have him try that.
Exit and go back in.
On the
Just either one, just try one. Just get online.
Hey, Mike, I was going to ask you while they're working that out.
Yeah.
Is there a web address or a link that we go to get to this, all the content? I came in.
Yes.
I may have missed it.
Yes. And so in the email, the welcome email that I sent,
Yes, sir.
there should be a link in there.
Okay. Cool.
That it's look for courses, your tech training is the link.
Okay, sounds good.
Yep.
I may have overlooked it, but I definitely got the email.
Okay, well, if you don't see it in that email, let me know.
All right.
Yeah, and I'll make sure that you get in.
Appreciate you, sir.
Absolutely. All right, so let's go ahead and let me go back to share my screen.
So we just follow along on your screen, right?
Yeah, that'd be,
Okay.
yeah, that absolutely.
It's still saying the same thing, even whenever he logged out and logged back in.
Yeah, I'm not sure what's happening there. I'll have to, are you in the same location now?
We're sitting, he's sitting right beside me.
Okay, so for now you could use the same device.
Hey, sir. You know what, my man? My brother on this side too. He's having an issue, man. He's waiting on another instructor. Your son might be in another instructor's class.
What's his name? I can check that right quick.
He's Roland Rodriguez. See, that's why I thought they probably messed up, because there's two of us. He has the same name as I do.
Oh, okay. So there should be 2 Rolands.
Yes, sir.
Okay,
Check
that's-
which is this instructor, bro.
Who's your instructor?
Mike Hogan.
Mike Hogan.
Yep. What about? So I've only got 1 in the class. I'll make sure that they get that updated.
That's probably what they probably thought it was, like a glimpse, I guess, where like the same person twice.
Yeah. Now what's his email address?
Tell them.
Trey Rodriguez.
Okay.
368 at yahoo.com.
Yeah, because I had to stop with guys.
So Roland Rodriguez 368 at yahoo.com.
No, Trey Rodriguez.
Oh,
Trey.
T-R-A-Y?
Trey.
E-Y. Okay. Good deal. I will send that and they will get that added. I bet that's the case. I bet they saw Roland Rodriguez and thought it was a duplicate. So we'll get that fixed.
Thank you, sir.
Hey, no problem. We'll go out to the chat just real quick. Yes, Justin, you asked about would we be able to watch this at a later time? Yes, you will. Absolutely. And like I said, you've already got a video of another class, but you will have access to this class as well. Okay, let's dive in. Now, I hate to start where we got to start, but we got to start with math. And a lot of people get excited about that. A lot of people, probably more people, say, I'm not really happy about math, but we're not going to dive deep into anything that's too strenuous. And so we'll be okay. Right? Everybody see math for electronics?
Yes.
Perfect.
Yes.
All right.
Yes,
perfect.
sir.
Good deal. Good deal. All right. So I'm going to make an adjustment
Just a
to the
math.
screen here. All right. So looking at learning objectives, 2 things we're going to try to do is we're going to talk about scientific notation, and we're really going to look at playing with scientific notation, whether I'm given a number and I need to convert that to scientific notation, or if I'm giving a scientific notation and I need to convert that back to a number. And so I'm going to be able to go back and forth one way or the other. And anybody dealt with scientific notation before?
Yes, sir.
Okay, good. Now, the reason we're going to really look at scientific notation and we're going to use this function is that when we're talking about electronics and when we're looking at some of these components that we're going to be studying over the next few weeks, some of their values are really, really large or really, really small, right? And so when I say really small, it may be a decimal point and 9 zeros before the first number, right? And so 9 zeros 2 5 might be an actual number that we're using. Well, it's hard to talk in terms of those values. It's hard to say, well, I'm dealing with a 0.00000000025, and so we've got to have another way to handle these numbers. And so that's where scientific notation comes in. Scientific notation, which we're going to look at the next few slides, gives us the opportunity of taking either a really big number or a really small number and representing it in typically a whole number times 10 to a power, right? The reason it's times 10 is because we're dealing with decimal, which is times 10, a base 10 numbering system. And so everything, when we talk about times 10, it's really just a movement of the decimal, right? And we're going to see that in just a second. And so this slide that has all of this on it. Like I said, I'm not going to read all these slides to you. You guys can go back and you can read the slide. But basically what it's saying is that we need scientific notation because we either have a really large number or a really small number. And we're going to represent that in a way that's easier for us to reference and easier for us to understand versus that very small or very large number. Here's a great example. So this number, 8,600,000. It's a number that we, in terms of size, well, we feel okay with that. And that's about what you guys probably bring home, a year, 8,000,006, right? And so what we want to do though is we want to convert this number, this 8,600,000.0. We want to convert that to something that has a whole number. Usually we'll go a whole number, a decimal place, and then another number. But it's going to be times 10 because we're base 10. And then we're going to raise it to a certain power. Now, that may look more complicated than it really is because this base 10 times the power is really nothing more than the number of times we move the decimal. And if you think about it, we'll get into this more when we talk about numbering systems. It makes perfect sense. Ones, tens, hundreds place, right? And so we get into each one of those weighted values. It's just times 10. It's times 10 more, right? And so we're going to take for a large number, 8,600,000. I'm going to take and I'm going to move my decimal. I'm going to see how many times I have to move it to get it to 8.6, right? That's what I really want, is I want a whole number on the left side of the decimal, right? So I'm going to get it all the way to this point. And so if I just count places, 1, 2, 3, 4, 5, 6, right? And so that gives me 8. I move the decimal here to now. So decimal 6, 8.6 times 10, and I moved it 6 places. So scientific notation, that's what we're going to call this, scientific notation. 8,600,000 is 8.6 times 10 to the 6th, right? It's not that hard. All we have to know is where the decimal starts, where we want it to end, count the number of places. The only other trick is which way we're moving the decimal, right? The way I like to think about it is if I start off with a very large number, right, 8,600,000, starting off with a very large number, well, this exponent is going to be positive. Because when I multiply this out, 10 to the 6th power times 8.6, I want to get 8,600,000. If I move the decimal the other way, if I start off with a very small number, we'll see what happens there. Actually, let's go ahead and let's take a look at another large number. So here we go. We've got an even larger number here. The process is still the same. I got to figure out where do I want to move the decimal. I want to move the decimal typically here, 3.68, and carry it out to the hundredths place, 3.68. Doesn't change anything. It's just, how precise I want to be. But if I'm moving it all the way to here, starting here, it's just a matter of counting, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 3.68 times 10 to the 10th. Moved it 10 places. Any questions? That's not that hard, right? Pretty straightforward. Pretty straightforward.
For sure.
Now, if we want to go the other direction, let's say that we want to move. We want to express a very small number. Both of those were large numbers. We want to express a very small number in scientific notation. Well, we're going to do the same thing. The process doesn't change. I've got my decimal. It's starting here. I want to move it all the way to here. Remember, I want a whole number on the left side of the decimal, so I want to move it all the way to this point. So I count 1, 2, 3. That's what we've done down here. 4, 5, 6, 7, 8, 9. So it's 4.7 times 10 to the 9th. Now, the only difference is, notice I have a negative 9. Keep in mind, this has to be the same value as this. You know, if I would multiply this out, I should get the same number. And so this is a very small number. So that means it's even smaller than, it's smaller than 1, right? Well, when we look at exponents, we know that any number raised to the 0 power is 1. So it's smaller than 1, which means that I have to start going in a negative direction. Now, if I start off with a small number, this exponent is always going to be negative. If it's a number less than 1, I'm going to have a negative exponent. If it's a number greater than 1, I'm going to have a positive exponent. Now, there are some people that will teach you, if you're moving the decimal to the right, it's going to be negative. If you're moving the decimal to the left, it's going to be positive. That's fine too. But instead of left and right, I just like thinking about, what am I starting with? If it's a very small number, then this has got to be a negative exponent. If it's a very large number that I'm trying to convert to scientific notation, okay, it's got to be a positive exponent. But the process is still the same. Identify where your decimal is, identify where you want to move the decimal to, and then count the spaces, right? So this is 4.7 times 10 to the negative 9th. Here I've got another number. Once again, smaller than 1. It's a small number, so I know I'm going to have a negative exponent. I want to move it all the way to this point. So I just count the number. It's 3.65 times 10. I moved it 6 spaces, 10 to the negative 6. Now, so that was going from a very large number or a very small number and converting to scientific notation. What if I'm given scientific notation and I want to go the other direction? You know, I want to convert it to the original number. For example, here I've been given 6.9 times 10 to the negative 6th. Now, once again, what I know about this exponent, that negative exponent means that this number is going to be less than 0. It's just the same process backwards. I write 6.9 down. I move the decimal place 6 places. Everything that's not a number already identified is zeros. I fill with zeros. And so there's my number, 0.00000069. Right? And so if I was, moving back and forth, I should be able to get this number and say I just moved the decimal 6 places. So that's going to give me 6.9 times 10 to the 6, a negative 6. Or if I'm given this, I can convert it back the other way. Not too difficult. We're going to see here in a second why it's important that we can move back and forth between the scientific notation and specific values. Here, I'm given a number 27 times 10 to the 3rd. Notice this is a little bit different because I don't have a decimal in between the 2 and the 7. It's actually here. It's important that I know where the decimal is, 27. We don't typically write decimals down with whole numbers, but we understand that it's right there. And so I'm going to move it 3 places. I'm going to move it. This number is going to be larger than 1 because I've got an exponent that is greater than 0. It's not a negative exponent. It's a positive exponent. So therefore, it's just a matter of writing down 27. And I'm going to move that decimal that's understood to be right there 3 places. And so I wind up with 27,000. Now, as we are moving into some of these components, what we'll do is we'll take that value, that scientific notation value, and we will add our prefixes. There's going to be a lot of information that we're going to understand about these components based on that scientific notation, right? For example, here we are. This is 10 to the 0, 10 being our base, right? Base numbering system 10 to the 0. Any power raised to the 0 is 1. And then as I move up, you're going to see I'm going to increase the size of the number. That means I'm adding 3 zeros. So I want 1 plus 3 more zeros. This is going to be adding 6 zeros, 1 plus 6 zeros, 1 plus 9 zeros, 1 plus 12 zeros. And then each one of those has a specific name. Some we're very familiar with, kilo, mega, giga, tera. You've probably heard all of those, especially with computers and the amount of data you hear, or memory. You hear a lot of those different terms talking about so many kilobytes, megabytes, gig, or even tera. Some of the new drives are not new necessarily now, but drives that are out, you may hear about terabytes of memory. And but you can see those numbers are large numbers. Some of those are extremely large. And what the scientific notation, understanding scientific notation, and then also connecting it to the prefix, and finally the symbol, that allows us to share a whole lot of information in a very compact way, right? I can talk about, if I had a resistor and it was, let's just say it was, 3.7 mega ohm. Well, in a short 3.7 capital M ohm, the unit ohm, I already know what all of that means. That's 3.7 times 10 to the 6, which means that's 3.7 with 6, actually it'd be 5 zeros because of 0.7, but it'd be 3.7 with 5 zeros behind the 7. That gives me that information, because I know what scientific notation is about. Now, one thing I will mention is you may hear engineering notation. Scientific notation, you can move scientific notation from any multiples. It could be times 10 to the 1, the 2, the 3, the 4, the 5, whatever. It's just moving your decimal place. In fact, let's see if I can go back and let's see. So that one's not a good one. It might not be a good example here. Oh, so we stay away from it. Okay. What I was going to say is, if you move, let's say you had a number and you converted it from a extremely large number, and you converted it to scientific notation, and you move the decimal place 11 spaces. Well, you could do that in scientific notation, because you're going to write it times 10 to the 11th power. But when we're dealing with engineering notation, the difference in the two, really, it's the same process, but the difference in the two is where we're going to decide to stop moving the decimal. If you notice, really what we work in are these multiples of 3, right? I'll move it 3 places, I'll move it 6 places, I'll move it 9 places, I'll move it 12 places. That allows me to stick to these prefixes, right? So instead of moving it 4, I'll only move it 3. So let's say, for example, go back. Just hold on one sec. Okay. All right, so let's say we had, a number that we're going to move 4 places. So it would be 0.00047, 0.00047. And so if we move the decimal place 4 places, that would give us 4.7 times 10 to the negative 4th, right? To the negative 4. Now that's scientific notation. The only thing is with engineering notation, we don't really move it to the negative 4th, right? What we do is we move it to as far enough so that we have a whole number on the left side of the decimal, right? And so we may have to move it 6 so that we get, instead of 0.4, we get 47 or 470. But it's going to be a multiple of 3, right? And we're going to stick to this notion of multiple of 3 so that we are working with kilo, mega, giga, tera, or micro, milli, nano, and pico. Now we get into some of the devices, the capacitors, even the inductors. We're going to see some of these very, very small values. So many picofarads with capacitors, and so we got to be able to operate with these numbers and understand what these numbers mean when we talk about something that is, because we're just going to put a number and we're going to put a small p, but we'll know, because we've dealt with it enough, that that's a really small number in terms of the mathematics. This is just another representation. Here we are at the decimal point, and as we move left or we move right, if I go 3, that's kilo, 10 to the 3rd. If I go 6, mega. If I go 9, giga. If I go 12, tera, and the other way as well. Milli, -3, micro. Now notice micro is this U with a tail on it, this Greek letter, right? So that's to the -6. Nano, small n, -9, and then pico, small p, -12. Here's an example. 8 times 10 to the 3rd. We convert that out. That's the same as 8 with a decimal sitting right there. I move it 3 places. I get 8,000. Well, in engineering notation, this times 10 to the 3rd is kilo, right? So 8, instead of writing out times 10 to the 3rd, I'm just going to write 8 kilo, 8K, right? You're going for, signed up for a local run, 5K, right? Well, what does that 5K actually mean? Well, that 5K is actually 5 times 10 to the 3rd meters, right? Or 5,000 meters. Scientific notation, 5.5 times 10 to the 6th. Right? We know this is a number that is much bigger than 1. I'm going to move this decimal place 6 places, which is going to give me 5, 5, and 5 zeros, or 5,500,000. But also know that this times 10 to the 6th is mega. So 5.5 meg, right? 5.5 mega. Working with numbers that are smaller than 1. 3.8 times 10 to the -3rd. The negative exponent tells me this number is going to be smaller than 1, right? And so if I'm going to convert it, I need to move this decimal. So to make that number smaller than 1, it goes from 3.8 to 0.0038. I'm converting to the value. If I'm converting to engineering notation using the prefix, times 10 to the -3rd is milli, right? So 3.8 milli. Same thing with nano. If I'm going 4.7 times 10 to the -9, I convert that to my whole number by just adding the zeros, moving the decimal 9 places, or 4.7 nano. So it's not that hard. It does take a little bit of time just getting used to moving back and forth. I will say it's also something that just because of everyday language, you find this, these values creeping in. You've probably got some familiarity with some of these prefixes. If you don't feel very comfortable with all of them, you probably feel comfortable with at least some of them. Now, if I wanted to do the math with some of these exponents, if I wanted to, work with, say, for example, here, I've got, 20, and I'm going to divide that by 10K. Now, there's a couple different ways we could do that. We know that if we're going to take 20, we're going to divide it by 10K. 10K is, 10K is times 10 to the third. I could add 3 zeros and actually just do the math, right? That'd be 20 divided by 10,000. And that would give me a number. And then I could convert that number back to engineering notation. That works. Sometimes that's one of the things I like about doing calculations with these circuits and components. Typically, there's more than one way to do something. And so it's easy to do something one way and then check it the other way, and to make sure that those two are equal and comparable. So you could do the long way. You could just convert this to 10,000, divide 20 by 10,000, come up with a very small number, create, and then translate that back to engineering notation. The other option is you could also work with these exponents. Now, 10K is 10 to the third. 20, we can look at the exponents there. It's 20. We said that any number times 10, or any number raised to a certain power is 1. And so this is the same as 20 times 10 to the 0, right? 20 times 10 to the 0. 10 to the 0 is 1. So 20 times 1 is basically what we're saying. And so what they have here is you can deal with just the bases, just the number itself, the values. And then you can also work with the exponents separately, right? And so you wind up with dividing 20, that's the value, divided by 10. It's pretty easy. 20 divided by 10 is 2. And then I can subtract, since I'm dividing, I can subtract the exponents. Now, the exponent for 20 was times 10 to the 0. And so I've got 0 minus 10K, the exponent of 10K. K is to the third, right? So if I take 0 and I subtract 3, I wind up with a -3, right? 0 minus 3 gives me a -3. And if you remember that chart on the previous page, -3 was milli. And so the answer to this drawn out problem is 2 milli. If I would divide 20 by 10,000, I'm going to get 2 milli, which is the same as 0.002, right? So like I said, you could do it either way. You can do the long way, 20 divided by 10,000, get 0.002, and then convert it to 2 milli. Or you could take a shortcut and say, I'm just going to divide my base value, 20 divided by 10, which gives me 2. I'll subtract my exponents. This was 0, this was 3. That gives me a -3. So I get 2 milli. Now, will we have to do a whole lot of that? No, we won't do a whole lot. It's just, be aware when you're working with exponents, there's 2 ways that you can deal with those exponents. We will have some formulas where we have to work with the reciprocal. The reciprocal is just taking a number, and if I want the reciprocal of that number, it's 1 divided by that number. Okay, and so if I'm looking, for example, here, this is 25 milli, right? If I take 1 and divide it by 25 milli, the reciprocal is 40. Typically on a calculator, you're going to see something that looks like a 1/x button, or even a x to the minus 1. Basically what you're doing is you're just taking 1 and you're dividing it by this number. To think about how the math works, 25 milli, we're talking about moving this decimal 3 places. Milli was times 10 to the negative third, right? So 1, 2, 3. So think about dividing 1 by 0.025. We know if we divided 1 by 0.25, we would get 4, right? So if I divide 1 by 0.025, that makes sense that I would get 40, right? For this chart, what they've done is they've said, okay, let's just get in the practice of taking the reciprocal of these numbers. So this is the reciprocal, and then let's represent that in engineering notation. 40, I can't move my decimal any direction to really represent, it's 40 times 10 to the 0. There's no prefix for that. It's just 40. So whatever the units might be, if we were talking about resistors, it would be 40 ohms. If we were talking about current, it'd be 40 amps, 40 volts. If we're talking about voltage, and so it's just 40. Now, if we do the same thing with 65K, right? 65K is a big number. We know that because K is times 10 to the third, which is 3 more zeros. 65K is 65,000. If I'm going to divide 1 by 65,000, I should expect a very small number. And you see, that's what I get, is a very small number, 0.000015385, right? And so this is, hey, let me punch it in the calculator. 65. By the way, when you punch it in your calculator will give you an option of putting in the prefix, times 10 to the x. And so you can put in 65 times 10 to the 3. 1 divided by 65 times 10 to the third. And so that will give you this small number. I am positive. And you guys, you tell me if you've heard anything different. Every once in a while, I hear something a little bit different. But what I've been told is there's no calculators on the TKT.
Correct. Yeah, I took it in a couple months back, and then there's no calculator, so it's just a sheet of paper and a pencil. You turn in your phone, your wallet, watch, hat, everything. You turn everything in. You just walk in. They give you a sheet of paper and a pencil, and that's it.
Yeah. So that's what I've been told. So therefore, in terms of the math, you got to keep the math pretty simple, right? And so don't look at this and think that you're going to have to go in and worry about the reciprocal of 65,000.
Okay, so it's going to be simple because
it absolutely. Do not freak out at this point over the math, right?
The worst thing about taking the test is the time.
The time.
The time is what gets you.
Yeah. I
think you get like an hour and a half for 90 questions or so.
Yeah, that's 1 a minute, right? I mean, you can't spend much time on it. Absolutely. So yeah, don't get caught up in the math. Don't, really right now in terms of the engineering notation, be aware of engineering and scientific notation. And we're going to use these prefixes enough through this course that you're going to feel very comfortable with the prefixes. So you won't have to worry about that.
Good deal.
Yeah. Don't panic.
Is this still two-part test or just 1-part test?
So everything I've heard is a 1-part test. Has anybody heard anything different?
Yeah, it's one and done.
Yeah.
Well, I don't know. Maybe I didn't get to the second part, so
I took the test.
I think I had heard that it was a 2-part test before.
Yeah, it was 2-part. I took the test like almost 20 years ago. I got through the first part, but there's a second part.
Okay. I tell you what, I'm going to take a note down. I'm going to see what I can find out about a second part for this test. The feedback I've had up to this point has always been 1 part, but I'll see if maybe if there's some second test, depending on which area you're going into, or I'll just see if I can get some more information on that. Yeah, so when we're looking at these, the values, the reciprocal, just, don't freak out about the math. Just make sure that you're kind of understanding what's taking place here. I'm taking 1, I'm dividing it by 65,000. I get this very small number. And then in order to convert that to engineering notation, I got to move the decimal. Now, here's a good example. Typically, when we were talking in the very beginning about scientific notation, and I was saying that, you want to move the decimal so that you get a whole number to the left of the decimal. So we would move this 1, 2, 3, 4, 5 places, and I'd say 1.53 times 10 to the 5th. That works, right? In terms of scientific notation, that does work. However, since we're dealing with engineering notation and we're working off of those prefixes that really are multiples of 3, instead of moving it 5 places, I'm going to go ahead and move it a 6th place so that now I can use the prefix micro, right? And so I'm going to move this decimal 6 places. It's going to give me 15 instead of 1.5. It's going to give me 15.385, but it's micro, right? If I move it 5 places, then I start getting into using a whole bunch of different prefixes, and I want to stick to really those multiples of 3 to cut down on all the prefixes that I need to use. And so you can see how that's a little bit different. That's a good example of only moving at 5, but for engineering, moving at 6. So I get 15.385 times 10 to the negative 6, which is actually micro. Other examples, 200 divided 1 by 200 to get the reciprocal, 0.005. I can move that 3 places. I get 5 milli. 0.1 micro, right? 0.1 micro. If I'm going to take the reciprocal of 0.1 micro, now remember, micro is times 10 to the negative 6. We typically would not do this. This is, we don't like starting a number with a decimal and using a prefix. I mean, if it was 0.1 micro, you might as well go ahead and move this to 9 spaces, and it would be 100 nano, right? But in terms of the actual value, it's the same. It's a really small number. I divide 1 by that small number, I'm going to get 10 million, which is times 10 times the 6 times 10 to the 6, which is mega. So 10 meg. We will have to, we've got some formulas that we'll have to use the reciprocal, but once again, everything will be kept much, much easier to do than some of this right here. All right, so we talked about scientific notation and engineering notation and those prefixes and being able to move back and forth between a large number, a small number, putting that into a notation where we can use an engineering prefix, and so therefore we can use either kilo, mega, or go in the other direction using milli or micro. That's what we're going to be working on, and when we're working with some of our components. Not very difficult, pretty easy to replicate, and we'll get a chance to do that. All right, so let's take about 5 minutes and just grab a sheet of paper, see if you can fill in any of or all of, see what we can fill in and just to see how we're doing. All right. So take the next 5 minutes and fill this in. You can do it on a sheet of paper at home, and then we'll talk about it. All right, what'd you guys get? What'd you get for this? We fill out this first chart. Start off with 5.1 times 10 to the 5th. We convert that to a number, a value. What do we get?
510,000.
510,000. Very good.
That's 10,000.
Great, great. What does that mean in terms of engineering notation?
510K.
510K, absolutely. Now, this is another one of those examples where we were at 5.1 times 10 to the 5th, right? And we didn't want it to the 5th. We want engineering notation, which is going to actually be to the 6th, right? And so when we move this decimal, when we get the value and everything, we move this decimal, you can see that it's not, we're not working with the 5th, we're working with the 6th. And so the number shifts slightly. All right, so what about the value, scientific notation value for this next one?
3.59 times 10 to the 6th power.
Yes, 3.59 times 10 to the 6th. I'm just moving my decimal, right? Very good. Then what about here? Engineering notation. If it's 3.59 times 10 to the 6th, what is that?
359 M.
Yep, 3.59 meg, right? Exactly. Very good. What about this last one? We started with engineering notation. We said 470 pico. What is that going to be in scientific notation?
4.7 times 10 to the negative 10.
So pico, 4.7 times 10 to, okay, I see what you did there. Yep. So it'd be 470. You could write it 470 times 10 to the negative 12th, or as you went to.
Yeah, that would make it easier. I was counting zeros back from the middle value.
Yeah. And that's a bunch of zeros. And you know, and that's the point. Those numbers get so big or so small. In this case, it's hard to deal with. Yeah, and so this number here is going to be, you know, a whole bunch of, you know, a bunch of zeros, right? We're going to see that in just a second. And then down here at the bottom, we had the reciprocal. We took 500. What was the reciprocal of that?
0.002.
0.002. Okay, 0.002. And remember, I'm taking 1 and I'm dividing that by this value. So 1 divided by 500 is going to give me 0.002. And in engineering notation, that would be so we got 0.002.
2 milli.
2 milli, exactly. I moved the decimal 3 places. And you'll get to see all these answers in just a second. I think that when I go to the next slide, it's going to show them all at once. And so that's why I'm holding off. Here we had the reciprocal, which was 0.01. Now, I don't think I mentioned this, but in order to get the reciprocal of the reciprocal, in other words, if you've had a number and you divided that number into 1, so you get this reciprocal. In order to get that number that you started with, well, all you do is divide it into 1, right? And so you just
100.
keep dividing into 1 and you'll get the other number, right? And so if I divide 1 by 0.01, I get
100.
100, exactly, 100. And if I take this number, this reciprocal 0.01, and I'm going to convert that to engineering notation, right? So if I was going to move my decimal, not 2 places, but 3 places, so that I can use engineering notation, I get
100 micro.
Okay, so So if I move it, I'm going, obviously it's going to be negative because this number is smaller than 1. And I'm going to move it 1, 2. 2 is not what I want for engineering notation. So I move it one more space. That gives me 10 to the negative third, 10 times 10 to the negative third, which is
10 milli.
10 milli, exactly. And then the final one, I start off with 25 milli. If I'm going to put that in, our decimal form, all I have to do is move my decimal back, right? And so I'm going to get 0.025. And then to get that value that we started with, the reciprocal, I just take 1, divide it by 0.025, and should get 40. So let's see if, okay, now it's going to make a liar at me. It's going to give it to me. We could have went through it all along. So I think this is pretty much what we said. Very good. Very good. Now, typically what we'll do in terms of each class, the way I usually run the class is, instead of giving you, a short break every hour, I kind of add the breaks up a little bit. And so when we get to a nice stopping point, we'll take about a 10-minute break, and then we'll come back. I think, let me just take a glance at what we got coming up. Okay, let's just take a look at, this is just because really this is the first video. I want to share this with you.
Guys, welcome back. I'm Mr. Wemp. This is Digital Electronics. We're actually going to be looking at one of our first topics, scientific and engineering notation. In digital electronics, we end up dealing with a lot of either very large numbers or very small numbers. And since we have these very large and very small numbers, they get kind of difficult to deal with. So we have scientific and engineering notation. Now, scientific notation shouldn't be anything new to most of you since you've done it before. So scientific notation basically is a way to take a very large or very small number and get into more of a bite-sized chunk. So we're all familiar with the 0.000009. Okay, and that number is way too small to be able to deal with. And so what scientific notation says is that we want a number to be between 1 and 9.99. Okay, so that's what we're looking for, is that number. Now this number is not a whole number that's between 1 and 9.99. Okay, so what do we have to do to make it do that? Well, we're going to have to move this decimal place. I'm going to choose a different color here. We're going to have to take this decimal place and we're going to have to move it over 1, 2, 3, 4, 5, 6, and right there is where a lot of people would stop, but that's 0.9, so we need to move a 7th. So we have 7 places. And when we move that decimal 7 places to the right, we're actually going to be saying that this number is now 9 times 10 to the 7th. And since we're going to the right, is it a positive or negative? Well, we're taking it and we take this 9 times 10 to the 7th. If we were to leave it positive, 10 to the 7th, we'd end up with all these zeros over on this side. So we're going to the right, so it's going to be a negative 7. Okay, so to the right is a negative number. Okay, now let's look at this same number again, but this time we'll look at, I don't know, we'll make it a huge number. So we'll take it and make it 9 with a whole bunch of zeros after it, so that we have this big giant number. Now, this number is obviously not between 1 and 9.99. So what am I going to have to do? Well, I'm going to have to take it, and I'm going to have to put my decimal in and move it 1, 2, 3, 4, 5, 6, 7, 8 places. So I have 8 places, and it's going to the left. Now, if I'm moving it 8 places to the left, basically what I'm going to end up with is 9 times 10 to the 8th. And because I'm going to the left, if I were to take this 9 and multiply it by 10 to the 8th, I would end up with this 9, I don't know what it is, 9 bazillion or whatever. I'd end up with this really big number. So if it goes to the left, it's going to be a positive. Okay? So there's our scientific notation and a couple of examples. Now, we use scientific notation quite a bit, but we use another type of notation, which is called engineering notation. Okay? And the engineering notation is basically the same thing as scientific notation, but we like to move things in threes. Engineers like to have 3 decimal places. So if we take that same number again, that 0.0000009, and then we're going to end up with a, well, we won't get to that point yet. We'll just leave that one off for now. So as we're looking at this, basically our engineering notation says that our numbers want to be between 1 and 999. Okay, so that's what we're looking for. We're looking for numbers that are between 1 and 999. So we've got this 0.000009, and we're also, so what are we going to do with it? We're going to actually calculate it out. Or not calculate it, but we're just going to move our decimal. So we're going to move decimal to the right, 1, 2, 3. So there's one group. Then we're going to move it 1, 2, 3. There's another group. Remember, we like to move in groups of 3 in engineering notation. And so what we're at 6 right now, but we are 0.09. That's not between 1 and 999. So we have to move again. 1, 2, 3. So that gives us our original 90. So what does that equal? Well, it's going to equal 90 times 10 to the -9. Okay, so basically what we end up doing is we're moving in groups of 3. So 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, now if we take a similar number, we go the other way. So maybe we have, this time we have a whole bunch of zeros after the 9. So it's this big giant number here. Well, what does that equal? Well, we're going to have to move our decimal again. So we're going to start here. We're going to move it in groups of 3. 1, 2, 3. And that's not between what we're looking for, so that's still much larger than 999. 1, 2, 3. Now we're at 9,000. Well, not bigger than 999. We're getting closer. Let's see if we can get it all the way there. So then we move 1, 2, 3, and now we're left with 9. So our number that we have is basically 9 times 10, and we move this thing 9 spaces to the left, so 10 to the 9th. Okay, so that's how we would mark that out. So what you might notice here is that basically we're dealing -9, 9. If we change this number around a bit, and we'll get something along the lines of, let's see here, where'd my pencil go? Okay, so if we change this number a bit, I go here and I put that many zeros, you'll notice it goes 1, 2, 3, and now it's 900. So that would equal 900 times 10 to the 3rd. So it goes 3, 6, 9, 12, both positive and negative. And those actually have some terms that we'll deal with. Let me move this down a little bit. And so what we can do is we can take that 900, and maybe we have 9 times 10 to the negative 3. So what would that be? Well, that would be 9, and then we move our decimal to the left. 1, 2, 3. So it'd be 0.009. No, excuse me, 0009. 1, 2, 3. So basically, nope, still wrong there. I'll get it. Don't worry. We'll get it eventually. We have our 9. We go 1, 2, 3. So there's 0.009. Okay, so that's our number. That would look like this. And what we can do is there's a scale, and basically 10 to the negative 3 is kilo. So 10 to the negative 3 is equal to kilograms, like kilograms, kilobytes, or excuse me, that's 10 to the 3. 10 to the negative 3 is milli, so I'm off here. So 10 to the negative 3 is like milli, like milligrams, millibytes, things like that. So this would be, I could take this and replace it right here, and so I would then have 9 mil of whatever, millibytes, milligrams, whatever. Okay, so if I had the same thing again, we'll do a little bit different color here just to make it a little different. If I had 9 times 10 to the 3, well, 10 to the third was kilobytes, so that can be swapped right in. So now I would have 9k of whatever I was doing. So we crossed that out and replaced it with the k. All right, so you can do that for all sorts of stuff. We deal with this mostly with resistors, where maybe we have 976,000 ohms, and we want to convert that into a smaller number that's a little bit easier to deal with. Okay, so basically that's your scientific and engineering notation. You even got a little taste of some of these pieces here. Just be prepared for some questions, to have some questions in class, and be prepared. We'll have a little activity, and also be on the lookout for some essential questions that you may need to answer. After you've watched this, you may have to do a little critical thinking. So, all right, well, that's the end.
So that gives you an idea of what the YouTube videos are like. Like I said, there are videos that have been curated over the last year or so. So some of them may cover the material in the same format. Some may cover it in a different way than the instructor does. But typically, there's some good information in those videos. What I was saying about break before I went to that video, usually what we'll do is we'll take a break about halfway through. You take about a 10-minute break, and then we will pick it back up and take our last break. Instead of kind of cutting the flow, what we'll do is we'll usually take our last break at the end of the class. So about a quarter till, we'll wrap up, and then that gives us, it's either your second break, or if you've got any questions, it gives it a little bit of opportunity there at the end of class to ask for somebody to ask questions, and I'll hang on for anybody who might have a question at the end of the class. So we'll take, like I said, 2 breaks, usually one about halfway and then one at the end. And so that brings us to, I think we're just about at the halfway point now. Looks like we're at, I guess, about 8:30 your time, or 8:25, somewhere around there. So let's take a break and come back at 8:45. How's that sound? Actually, let's change that. Let's take a break and come back at 8:40. That's what I meant. Right. So just a few minutes over 10 minutes, and then we'll come back and we'll finish up in the last hour or so. All right. So 8:40. That's the right time for most of you guys, right?
Yes, sir.
Okay. Okay. Good deal. Good deal. All right. So we'll see you in about 12 minutes. Okay. So let's take a look at electricity. Roland, just to let you know that I reached out during the break to try to get that second account straightened out. And so they're working on adding that second account. So hopefully we'll have that taken care of before the night's over.
Thank you, sir.
You're welcome. You're welcome. All right, so let's take a look at electricity, and I'm skipping around a little bit just because the math can get a little boring after a while, and so I just want to kind of move around a little bit. We can always go back and pick up some more of the math, and really it's about exponents and continuing to work with exponents and working with proportions, things of that nature. But we're going to do a lot of that when we get into our discussion of some of these formulas as we're using. Hold on one sec. Sorry about that. All right, Roland, that second account should be good to go now. See if you can log in now.
We're trying right now.
Okay. All right, just let me know. All right, so we're going to go ahead and we're going to take a look at electricity. Can you guys see introduction to electricity? Can you see that slide?
Yeah.
Okay,
Yeah.
great. Perfect. All right, so what we're going to do, hopefully, we're going to talk about atoms. We're going to look at the different parts of an atom. We're going to talk about those electrically charged parts of an atom. We're going to talk about some specialized electrons and those electrons that really will determine kind of the material, whether it's a conductor, a semiconductor, or an insulator. And so we're going to work through those things. We're going to talk about a different, electron current flow, Coulomb's law, talk about voltage and potential difference, electromotive force, and then we're going to give some common definitions and understanding. We'll look at some schematic diagrams for chassis ground and earth ground, and we'll talk about what an open circuit and a shorted circuit could be. All right, so we'll work through quite a few things as we move through this basic electronics. Now, hold on one second. I'm going to check the chat. I see where Justin put out there, be setting up a study group on chat. That's great. I mean, you guys, the more you get together and can talk it out behind the scenes, the better off you're going to be. So kudos to that. All right, so let's continue on with electronics. We're talking about matter. Anything that has weight occupies space. Solid, liquid, gas. That's typically what we're talking about in matter. There's elements. We all are familiar with that. Elemental chart. Those basic building blocks. Basically when you're talking about those pure components, those pure elements that are made up just of those elements. That periodic table. Then when you talk about a compound, you start putting some of those elements together, right? You combine a couple of those elements and you make a compound. For example, water there, H2O. So you've got hydrogen, you got oxygen in different quantities that gives you that water. The smallest particle, the smallest piece, the smallest unit that you can have and still have the characteristics of the compound is a molecule. So if you got a molecule of water, it's still 2 parts hydrogen, 1 part oxygen. So it's still water, right? So you got elements that are those individual different natural occurring, most of them at least, those different elemental table, that periodic table. And then you've got compounds, which are multiple of those, and then a molecule, which is the smallest unit you can have and still be a compound. All right.
He's still not able to log in.
Still not able to? Okay.
No, sir. It just said the host has another meeting in progress. I'm sorry.
Oh, okay.
Are you using the same login on two different devices, or are they separate logins?
Separate. He's on his own. He has his own little. They gave him an email on his own IP address and everything for it.
Yeah. So I wonder if, and let me go out and see if I can see anything in the waiting room.
Justin just pasted the link too in the chat.
Can you try to hit that link? Roland, were you able to use that link in the chat? Did that help?
I just copied it and sent it to him. He's right beside me.
Oh, okay.
He's in.
Awesome. Great. I'll let him know.
Appreciate it.
All right, good deal. All right, so and let me just gonna clean that up a bit. All right, so we're talking about atoms, right? This smallest particle of an element, right? So when we're talking about this atom, you got a nucleus, which is really the center part. That's the area that contains most of the weight, if you will. We got the electrons that are around the nucleus. They are in these, what we're going to call orbits. They are can be removed from these orbits depending on some things that we're going to take a look at in just a minute. But inside that nucleus, going back to it, you have neutrons and protons. So electrons, neutrons, and protons. Protons, positive charge. Electrons, negative charge. Neutrons, no charge. Same weight as the proton, but no charge, right? And so really, when we think about electricity, it's those electrons that we're focused on. Those negatively charged electrons is really what we're going to be talking mostly about. And we're going to look at materials that have those negatively charged electrons that are to conduct. We can move those electrons easily. For insulation, it's going to be materials that have tightly bound electrons in those orbits or those shells. There's an example. We've got our nucleus in the center. Inside that nucleus, you've got our protons and neutrons. And then around that nucleus, we've got these shells. And you can see electrons in each one of these shells. Now, notice that we have one electron in this outermost shell, which we'll call our valence shell or our valence orbit. The outermost orbit outermost shell, there's only one electron. And what that means is this one electron is loosely held. You know, it is easy to cause this electron to move from this atom to another atom. You know, if I have a valence shell that has 8 electrons, then they're much more tightly held. They tend to avoid being removed from that shell, and therefore they avoid moving electrons from atom to atom, which means that they avoid moving negative charge from atom to atom, or as we refer to it, they avoid moving electricity down that material. So if you have an insulator, you know, it really is hard to get electricity to flow in that insulator. It's because of the properties that are associated with holding these valence electrons so tightly. You know, if you've got a material that you use as a conductor, you know, wiring that we're going to use to conduct electricity, well, those are materials that have one valence electron, and so that electron is loosely held and can move from atom to atom relatively easily. And so that's what we're talking about here in terms of that outermost shell. If I have 3 or less, we're looking at a conductor. You know, there's a lot less energy that's required to move those electrons from atom to atom to atom, or to remove that electron from the particular atom that it's in. That's a conductor. An insulator, you know, 5 or more valence electrons, those are tightly held, and those, you know, it takes a lot of energy to cause that electron to move, and so therefore it doesn't conduct. You know, obviously it's not a conductor, it's an insulator. It doesn't conduct electricity very well. You'll see a lot of these materials used for safety materials versus used for conduction. If you look at some of the examples, a conductor, obviously what we know, gold, silver, copper. You look at insulators, you know, ceramic, rubber, very common to use those. And then if you're right in the middle, so you've got 4, so it's not 3 or less, so it's not a conductor, it's not 5 or more, it's not an insulator, you know, it's 4, it's a semiconductor, which has this unique property of being able to conduct once a certain potential is overcome. And so what we're going to find is we're going to use these semiconductors almost like switches, where we can have electricity once we get above a certain potential. We have you know, electricity that will be conducted, but up until that potential, no electricity is conducted. And so we'll see silicon is the most popular. Germanium is also used, but we'll talk about both of those materials when we get to talking about semiconductors and transistors and p-n junctions with diodes and things of that nature. You can see down at the bottom, those 3 bullets, conductors. Small amount of energy is needed to cause that electron to move from atom to atom. Semiconductor, a moderate amount of energy is needed. Insulators, a large amount of energy is needed. Now, Coulomb's law, we talk about Coulomb's law, and you know, really what we're talking about here is the fact that like charges repel and unlike charges attract. And you know, this is you may not walk around stating Coulomb's law, but it's not something that is necessarily foreign to most of us, because at one time or another we've all had magnets, and I'm sure you've taken magnets and you've put the positive end of a bar magnet close to the negative end of another magnet, and snap, they go right together. And then the very next thing that you do is you flip one magnet around. And so now you've got the positive side of one magnet, and you try to push it together with the positive side of the other magnet. And you can tell there's that resistance. It just doesn't want to go together. I mean, it feels like there's something in between those two magnets. And it's those charges that are repelling one another, that are pushing against one another, right? And so like charges repel, unlike charges attract. Now, the reason this is going to be important for us is because we're talking about these electrons and this notion that we have atoms that have these electrons in these valence shells, and we're going to cause these electrons to move. And we know these electrons are negatively charged, right? And so just by the use of Coulomb's law, if we think about Coulomb's law, and if we've got a battery that has a negative terminal and a positive terminal, and we connect a conductor, and we saw that copper was a great conductor. We know that it's a great conductor, but we also saw from a valence electron standpoint, it has one valence electron. So therefore, it doesn't take a lot to cause that valence electron to move from atom to atom. And when we connect a battery to this copper wire, what happens is those valence electrons that are negatively charged, based on Coulomb's law, those negatively charged electrons will be repelled from the negative side of our battery and attracted to the positive side of our battery. And so we see electrons that would then begin to move, because we have this different potential from one side of the wire to the other side, negative versus positive. Those negative electrons are pulled toward the positive, they're attracted toward the positive, and they're repelled from the negative. So they're pushed, in one sense, and they're pulled in the other sense. Attracted toward positive, repelled from negative. And so that's Coulomb's law. When we think about Coulomb's law, that's really what we're talking about, is understanding these charges and understanding the makeup of that atom and those electrons, and how they will act with those forces at play. Now, I'm sure that we'll get into it here in a minute, and I'll just repeat it once we get there. But when we talk about electron current flow, so we're talking about electrons that are moving in a circuit, and we'll call that electron current flow. We'll call that current. If you look at this first paragraph, it talks about the symbol for current being an I, right? I know that seems a little odd, but the symbol for current will be an I. The easiest way to remember that is think about intensity. We're going to measure that in amperes. So an A, right? And so we're going to have so many amps, so many amperes of current in a particular circuit. For the most part, if we were in a lab setting where I would have you guys build circuits and we would test those circuits and take measurements, we would be dealing with very small currents. We would work typically in that milliamp range of current, just to avoid any danger in terms of electrocution and shock. But when you start talking about currents can get very high, and we'll talk about in our safety slide as well, once we get there, the difference between voltage and current. And I'm not going to tell you that voltage is not dangerous, because they play together, right? The more voltage you have for any given resistance, the more current you're going to have. But it's that current that flows, through your body that is going to be the truly is going to be the impact that causes harm. Voltage by itself is just potential difference. But what I wanted to get at, what I mentioned that I would say, and I'd probably say again, when people talk about current, you may hear people talk about different types of current. You may hear electron flow, you might hear conventional flow, especially if you get around folks who are dealing with theoretical electronics and they're doing a lot of research. You may hear this notion of conventional flow, and they really look at current flow being positive to negative versus negative to positive. In this course, for our purposes, we're always going to talk about electron current flow. Electrons which are negative, they're repelled from the negative side of the battery, they're attracted to the positive side, and so it's negative to positive current flow, right? Electron current flow, negative to positive. But there is this other mentality that does exist, that and there's a deeper reason for that as well. But for us, we're just going to really focus on electron current flow. I think that keeps it easiest for us when we're talking about components and we're talking about troubleshooting and those things. So moving on from current, looking at voltage, or what we may call EMF, or electromotive force. Right? It's a potential difference. Right? It is the difference of potential between two different points. If you think about a battery, well, I've got two terminals on that battery, and there is a difference of potential between those 2 points. One is negative, one is positive. If those batteries are at the same potential, then that battery is not going to do anything in the circuit. That battery, those two terminals have to be at different potentials in order for one to be more negative and one to be more positive. And when one is more negative, one is more positive, you have that difference. Well, that difference is measured in voltage. Right? So that's we're going to measure with V, or you may also see it as E. Right? And so voltage, or E, short for electromotive force, it's going to be the volt that we're going to measure in. So that's pretty easy to keep straight, but you will see that E. And even, I'll say even in this course, you're going to see slides that reference voltage as V, and you're going to see slides that reference voltage as E. So, and that's probably a good thing. Probably gets you used to both of those uses. Okay. Circuit. So current in the circuit increases or decreases in direct proportion to the voltage, EMF applied to the circuit. The bigger the push, the more that gets done. So I'll give you an analogy, and here's the thing about analogies. It may help you, it may not. If it doesn't, just don't worry about it. But you can just let it go. If we think about water and current and voltage, potential difference, if you were standing on a bank beside a river, water that was flowing, if there's very little difference from the high point to the low point, right? And so if there's very little difference of potential, then you would expect the water to be moving at a slow pace, the intensity, the current, to be rather slow. As you increase the difference from the high point to the low point, so in other words, as the water, between the top and the bottom, it gets steeper, right? As you increase the difference in potential, you would expect the intensity of that water to pick up, the current to increase. I mean, all the way to the point where you could do the extreme if you had a waterfall, right? So now I have a high point and a bottom, a low point, and so I've got a pretty large potential difference between the top and the bottom. That water that's falling now has flows with a lot of current. It flows with quite a bit of intensity. And so that really is what's happening in these circuits. When we have, difference of potential, it's not so much elevation as the river, but it is negative to positive. These charges, the negative charge, positive charge, as we increase the difference of potential, so maybe it's not 1 volt, but maybe it's 10 volts, or maybe it's 100 volts, or maybe it's 1,000 volts. As you increase the voltage, that's increased the potential difference between the two terminals. Well, that increases, that's the same as increasing the elevation, high to low with this water that would be flowing. And so the increase in voltage, the increase in potential difference comes with an increase in current, provided that basically the resistance remains the same. What I mean by resistance, we're going to look at components that we can put into these circuits that give a certain amount of resistance, so it will control the flow, if you will. So imagine that we had that same river. We had a potential difference top to bottom, and so we had some current flow. And then I put a dam in that river. So now I can control the flow of that circuit. I can control the flow of that river. Well, when we look at resistors, that's what we're going to be able to do with resistors. We could have a fixed resistor that is going to give a certain amount of resistance, and so that would be us damming up a portion of the river, and so it would slow down flow. But as I still increase my potential difference, I would get an increase in current, but just not the same if there was no resistance there at all. Or I could have a resistor that is variable, and so I can control it. And now I could turn up how much I want to resist or turn down. And all of that we will take a look at when we get into components. But the piece that you need to understand is that my potential difference and the current are related. And in fact, they're directly proportional. As potential difference increases, my current increases. As potential difference or voltage decreases, my current decreases. And then the resistance is the third factor in that formula that we're going to talk about, I'm sure, relatively soon. So here we have a circuit, basic circuit. Talks about two basic requirements for current flow. Not a big fan of that statement, but okay, we'll go with that. The reason I'm not a big fan of that statement is, so it says we need a source. This is a battery. Notice the small bar here and the larger bar. The small is always going to be the negative side of the battery. This is the negative terminal. This is the positive terminal. And so it says we need a source. We've got a source. It says we need a complete closed loop, right? And so I have to have a loop that goes all the way around. If I've got a break in that loop, then current cannot flow all the way. And so it's not going to flow at all, right? It's not going to flow through the circuit. Now, the reason I said I don't really like the way this is stated, there are two basic requirements. There's actually a third component here, this resistor. This resistor provides some resistance for current flow. And technically, the right current would flow without this resistor. However, what's going to happen is it's going to flow extremely fast. There's going to be a lot of current. And more than likely, there's going to be damage to this conductor eventually. A great example of, and I don't know if anybody else has ever done this, but I have done this. I used to work in a hospital environment, working on medical equipment, and some of our patient units had telemetry, and they, basically a telemetry unit. It allows the patient to get up and move around while you're still monitoring the patient. They've got a transmitter that takes a 9-volt battery, and often it's as simple as the battery has just gone out, and so you go up and you always carry extra batteries with you. And I've tossed a battery in my pocket before, a 9-volt battery, and if you've got any change in your pocket and a 9-volt battery, those terminals, they tend to get together, and you find your pocket getting really hot really quick. And so, yes, technically it's true. There's 2 basic requirements. You would get current flow, but we're always also going to have a resistor to limit current in this circuit. And I mean, typically there's a reason for this circuit in the first place. And so whether this is a representation of a resistor to limit the amount of current flow or just the load itself. So you're going to have that load. And I think we'll see something that actually includes that later on. Now, the other thing is we always talk about this flow being an electron current flow being negative to positive. Remember what we said about Coulomb's law, likes repel. So I've got these negative electrons that are in this copper wire, and they're all made up of those atoms that have that one valence electron that's just dying to be removed and go somewhere else. And so they don't mind traveling from atom to atom, but they need a little encouragement. And whenever this negative is placed here, those negative atoms are repelled from the negative based on Coulomb's law, and they're also attracted to this positive sitting on the other side. And so they're pushed from this side, and they're pulled from this side, pulled to this side, I guess. And so you get that electron flow, and that flow is going to be the same through this entire circuit, right? And so it's not gonna be really fast here, slow down. It's not going to be, as you get further away, it's going to be less. And as you get closer, it's going to be more. For this particular type of circuit, we'll start naming circuits as we get it a little bit further in, but you're going to see that this current flow is going to be the same throughout, always negative to positive, right? Negative to positive. Electron current flow, negative to positive. Oh, there you go. So this electrical circuit consists of 3 parts: a source, a conductor, and a load, right? And so there's some reason we've got this circuit. So we've got this is a bulb out here that we're going to have this bulb turn on. We've got a source here, negative, positive. This is a switch. We've closed the switch and we've completed the loop. The conductor will conduct negative to positive. It'll go through the load or through this LED. This LED will light as long as this switch is closed. When the switch is opened, LED is going to cut off because I no longer have a completed circuit, therefore no electron flow. As we're looking at schematics, when we go through, we'll identify ground. Ground could be for safety purposes. It could be an actual earth ground, where if you look at your house, you've got your electrical system that is grounded. Usually is connected to maybe a cold water pipe that is actually obviously running into the ground. Serves as a great way to allow electrons to flow as opposed to flowing through if you had an alternate path. What we really want to do with ground is ground these circuits so that if for somehow you got across a circuit and you were a secondary path for current flow, there was still a path to ground that was less resistance than you. And so you've got this earth ground, which looks like a stake that goes into the ground. You've also got this chassis ground. A chassis ground, now sometimes it may not be connected to, it may be a reference point. You know, a lot of times a chassis ground, when you're talking about equipment, especially if you have equipment that is double insulated, that's, you know, plastic, it may just be a reference point in terms of the chassis ground. When we talk about ground, you know, typically we're thinking about, you know, safety purposes or reference points. Looking at an open circuit or a closed circuit. If we have an open circuit, you know, this circuit, and we saw this before when we had a switch, right? We had a switch up here, and when the switch was open, we did not get electron current flow through the circuit, and then we closed the switch. Well, that's the same thing that happens. It's just that we don't have a switch. We've got an open for some other reason. You know, maybe a conductor was damaged. You know, who knows what happened here? But you've got electrons that will not flow, and so therefore I don't get any current flow in this circuit because I have an open in this circuit. If I have a short circuit, you know, a short circuit or a shorted circuit, we're talking about a circuit that now provides a secondary path for current to flow. Well, this secondary path, instead of electrons going in the path they should, you know, through this resistor and back to the positive side of the battery, because, you know, maybe someone has dropped a paper clip in this device or whatever it may be. Now we have a secondary path, so electrons will go through this path and back as opposed to going through the load. And what happens is you're going to have an increased current flow in this area where you have the short, because it's not an intended path for current to flow. You know, usually you've got some safety feature that will detect this short circuit. You know, maybe it's a fuse, maybe it's a breaker, and you know, it's going to detect the increase in current flow and say, "Whoa, something's wrong. You know, something has shorted out my load. Let me go ahead and open this circuit up." So if I had, let's say I had a breaker wired in here. So as soon as the breaker realizes that the current is too great, the breaker trips, opens the circuit, and now I've got no current flow because I've got an open circuit here. Even with the short here, I've got an open circuit. So, you know, have a safe condition again. Electrostatic discharge. You know, this is always fun. You're sliding around, getting charged up, and, you know, touching somebody, and then boom, you give them a shock. It's surprising how high, in terms of voltage, those discharges can be. I mean, they can be fairly high. You know, the deal is, it's not a whole lot of sustained current, and it's certainly not enough to, you know, do any damage other than some, you know, small direct pain. You know, it's more prevalent in cool, dry climates. You know, basically, what we have to worry about in terms of electrostatic discharge is you want to make sure when we start working with some of these components that we take precautions to avoid any charge buildup. Because if you're working with, say you start working with integrated circuits or microprocessors, and you know, a discharge, you know, 3,000 volt discharge to a semiconductor or to a microprocessor, while it might not cause it to immediately fail, it's certainly going to do some damage. You know, it's not good for it. And so, you know, we'll take precautions, like we'll use static straps, anti-static straps on the floor, static straps on your wrists, maybe even on your desk. We'll use electrostatic safe tools, really anything we can to make sure, we'll make sure that whatever we're working on, you know, the case has been grounded, we'll make sure that, we don't have any buildup difference of potential between the device and, the tools or ourselves, just to make sure that we're not going to provide, some means for electrostatic discharge when we're working with some of this, equipment that can be, like I said, once we get into the ICs, can be, it could be negatively impacted by electrostatic discharge. If you had a discharge across a resistor, it's not going to do any damage. A capacitor, it's not going to do anything to a capacitor. However, if you're talking about, like I said, some of these integrated circuits where the circuitry is so small, it could do some damage. All right, so that's some of the basics of the diving into electricity and thinking about what we're going to be in for the next couple weeks in terms of looking at electricity and that makeup and how we can control and how we can use those electrons that we want to move through these circuits and through these different components, and how we can, what we're going to get into is how we can use this movement of electrons and put them in a bunch of different types of circuitry to do some different things. We're definitely not getting into electrical design, but we're going to take a look at a couple different circuits and how we can use those circuits, especially in terms of a power supply, and what signals will look like and how we can determine if it's working the way it should, and how do we troubleshoot these components and some basic devices. Okay. By the way, at the end of the PowerPoints, there are usually some quiz questions like this. For example, define the following terms. It gives you an opportunity to go in, define those terms, and it'll give you the answers on a following slide. Some of those, like the table that we did earlier, I'll go over. Some of those, I think it's good for you to go back and review the PowerPoint and just make sure that you got a feel for each one of these terms. And so I won't go over all of the questions at the end of each presentation. All right, so let's see. All right, questions about basic electricity. All right, usually silence means that I did a really good job of explaining it, or I completely missed the mark. So I'm sure I'm somewhere in the middle there.
No, no questions for now, man.
Okay, good. Let's see. I want to go back and I want to pick up, just hit a little bit more of the math. Okay, as you're going through this session one, you're going to see one area that talks about proportions. And, especially when we're looking at Ohm's law, when we're thinking about, the three components that we've two that we've talked about, one that we've kind of talked around, voltage, that potential difference, current, that intensity of flow, and then resistance. So we have Ohm's law that indicates that voltage is equal to current times resistance. And so it's this formula, right? But instead of, let me do this. This will not be pretty, but let's see. Voltage is equal to current times resistance. All right. So it's really this formula, X, Y, Z, X equals Y times Z, but it's voltage is equal to current times resistance. And so we're going to see this formula, voltage is equal to current times resistance, over and over and over until you guys, have no problem with Ohm's law. That's what we're going to call that, Ohm's law, right? And when we think about Ohm's law, we said that if I increase the potential difference, remember we were talking about our river as the water is flowing by and we're standing on the bank. As I increase the elevation, as I increase the potential difference, my current will either increase or decrease, right? If I increase my potential difference, my current will increase, right? So if I'm standing on the bank and there is no difference, if it's a level playing field, as I go from no difference to elevating the high side and lowering the bottom all the way up to what would be a waterfall, so say there's hundreds of feet of difference between the two, my current is going to do the same thing. As my voltage increases, my current is going to increase. Now, that is what we're talking about when we say directly proportional. We're talking about two components that are directly proportional. As one increases, the other will increase. You can see here they're talking about with X, Y, Z in terms of dependent variables and directly proportionate and independent variables. Given Y or Z increases, then X will increase. If I increase my current, well, my voltage must increase for that to be true, right? And we're going to talk about those two being directly proportional throughout this entire course, because for any given resistance, as voltage increases, current's going to increase. Same thing happens if my voltage decreases, my current is going to decrease. So when we say directly proportional, basically what we mean is they're moving in the same direction. As one increases, the other is going to decrease, right? Now, another way I can write that formula is I can change this formula around and solve it for current, right? Right now it's solved for voltage. Voltage is equal to current times resistance. If I solve it for current, I would do that by dividing both sides by R, right? If I divide this side by R, they cancel out. If I divide the other side by R, I'm left with current is equal to voltage divided by resistance, right? So that's still Ohm's law. It's just now it's solved for current. And the reason I wanted you to see that is because when these variables are on opposite sides of this fraction, this would be numerator, denominator. This would be in the numerator. This is basically over 1. What it means is that they are inversely proportional. What inversely proportional means is as one increases, the other will decrease, right? So if I have voltage, and let's just say I leave voltage the same, and I increase the amount of resistance, well, that means I'm dividing the number that hasn't changed by a larger number. Well, that means I get a smaller number, right? Like, let's just put some numbers in here. Let's say that this was 10. Let's say that this equals to, I need to get a pad that I can draw this on. All right, so let's say it was that 10 volts over 1 ohm. And so 10 divided by 1, that's going to give me a current of 10 amps, right? 10 divided by 1 is 10 amps, right? So my current would be 10 amps. Well, if I increase, let's say I increase this, instead of 1, let's say I increase that to 10. Now 10 volts divided by 10 ohms, I got 1 amp. So it went from 10 amps to 1 amp. And my point being, those two are inversely proportional. Directly proportional, current's going to go up, voltage is going to go up, right? You can see same thing is true here. With this formula, nothing's changed. I moved the formula around just so you can see it a little bit better, but nothing's changed. If my resistance remains the same, I'm still going to get, as my voltage increases, I'm going to divide it by the same number, my current would increase. And so that relationship is still directly proportional. But when I look at voltage, I look at current and resistance, the difference between current and resistance, those two will be inversely proportional. If I have a circuit, if I increase the resistance in the circuit, I'm going to get less current flow. That's always going to be the case. And so that I just wanted to see you that, talk about that difference between directly proportional and inversely proportional. By the way, that's Ohm's law. This formula, R total, R1 plus R2 plus R3, is actually the total resistance of a series circuit. All right, we're going to see that. I think we'll get into that on Wednesday. If I have a circuit and I have multiple resistors, I can add those resistors together to get the total resistance of the circuit, the series circuit. Question about direct or inversely proportional. Okay, let's just see. You can see right there is the exact example, and it's even done a little bit nicer. You don't have to deal with my drawing. Current is equal to voltage divided by resistance. That's what they're showing you there. Current is directly proportional to voltage. As my voltage increases, my current will increase, given that resistance stays the same. Inversely proportional to resistance. As my resistance increases, given voltage stays the same, my current is going to decrease. All right. Good deal. Let me back up to session 1. Let's see. I think we're good there. All right. So we'll take a look at this quick video. I say quick, I'm not really sure how long it is. We'll take a look at this video, and then we'll see what we got after that.
All right, now we're going to talk about the idea of an electric current. And the story about current starts with the idea of charge. So we've learned that we have two kinds of charges, positive and negative charge. We'll just make up two little charges like that. And we know if they're the opposite sign, that there will be a force of attraction between them. And if they have two like signs, here's two charges that are both positive, and these charges are going to repel each other. So this is the basic electrostatics idea. And the same thing for two minus charges, they also repel. So like charges repel and unlike charges attract. That's one idea. So we have the idea of charge. And now we need a place to get some charge. And one of the places we like to get charge from is copper wires. A copper atom looks like this. A copper atom has a nucleus with some protons in it, and it also has electrons flying around the outside, electrons in orbits around the outside. So we'll draw the electrons like this. So there'll be orbits around this nucleus. Pretty good circles. And there'll be electrons in these. Little minus signs. There's electrons stacked up in this. And even farther out, there's electrons. So there's a kind of a interesting looking copper atom. Copper, the symbol for copper is Cu, and its atomic number is 29. 29. That means there's 29 protons inside here, and there's 29 electrons outside. And it turns out, just as a coincidence for copper, that the last orbital out here has just one electron in it. That guy right there. And that's the one that is the easiest to pull away from copper and have it go participate in conduction, in electric current. So when if I have a chunk of copper, every copper atom will have the opportunity to contribute this one lonely electron out here. If we look at another element, like for instance silver has this same kind of a electron configuration where there's just one out here, and that's why silver and copper are such good conductors. All right, so now we're going to let's build a copper wire. Here's sort of a copper wire. It's just made of solid copper. It's all full of copper atoms. And I'm going to put a voltage across this. There's our little battery. This is the minus sign. This is the plus side. And we'll hook up a battery to this. And what's going on in here? Inside this copper is a whole bunch of electrons that are associated with atoms. It's a neutral piece of metal. There's the same number of protons as there is electrons. But these electrons are a little bit loose. So if I put a plus over here, that's this situation right here where a plus is attracting a minus. And so an electron is going to sort of wander over this way and go like that. And that's going to leave sort of a net positive charge in this region. And so these electrons are all going to start moving in this direction. And then at the end, here, an electron is going to come out of this battery, travel in here, and it's going to go in there and make up the difference. So if I had a net positive charge here from the electrons leaving and going to the left, this battery would fill those in. And I'm going to get a net movement of charge, of negative charge, around in this direction like this. The question is, well, how do I measure that? How do I measure or give a number to that amount of stuff that's going on? So we want to quantify that. We want to assign a number to the amount of current happening here. So what we do is in our heads, we put a boundary across here. So just make that up in your head. And it cuts all the way through the copper. And what we know, we're going to stand right here. And we're going to keep our eye right on this boundary down in here. And as we watch, what we're going to do is we're going to count the number of electrons that move by here. And we're going to have a stopwatch, and we're going to time that. And so we're going to get, basically, this is charge. It's negative charge, and it's moving to the side. And what we're going to do is at one little spot right here, we're just going to count the number that go by in 1 second. And so we're going to get charge per second. And it's going to be a negative charge moving by. And that's what we call current. And it's the same as water flowing by in a river. That's the same idea. All right, now I'm going to set up a different situation that also produces a current. And this time we're going to do it with water and salt. So here's just, let's build a tube of salt water like this. So we're going to pretend this is some tube that's all full of water. I'm also going to put a battery here. Let's put another battery. And we'll stick the wire into there, and we'll stick the wire into there. And this is the plus side of the battery, and this is the minus side of the battery. So water is H2O, and this does not conduct. There's no free electrons available here. But what I'm going to do is I'm going to put some table salt in it. This is ordinary salt that you put on your food, and it's made of sodium. That's the symbol for sodium, and chloride. Cl is chloride. Sodium chloride is table salt. If we sprinkle some table salt into water, what happens is these dissolve, and we get a net plus charge here and a net minus charge on the chlorine. So out here is floating around NAs with plus signs and Cls nearby, really close nearby, with minuses. Let's keep it even, all right? Now, when I dip my battery wires into this water, what's going to happen is this plus charge over here from the battery is going to attract the minus Cls. So the Cl is going to move that way a little bit. And over here, the same thing is happening. There's a minus sign here. There's a minus from the battery. And that's going to attract this, and it's also going to repel the Cl minuses. And so what we get is a net motion of positive charge plus Q going this way, and we get minus Q going this way. And how do we measure that current? How do we measure that current? Well, we do it the same way as we did up there with copper. We put a boundary through here in our heads. We stand here and we watch the charges moving by. And what we're going to get is some sodiums, NAs, moving this way, and chlorines moving this way, just like we showed here. Na moving this way. And so there's going to be plus charges moving through the boundary and minus charges moving through the boundary in the opposite direction. And if I take the total sum of that, for example, if I see one Na go this way and one Cl go this way, that's equivalent to 2 charges moving through the boundary. Hope that makes sense. It's equivalent to 2 charges, one going this way and one going this way. And because they have opposite signs, they add together and make 2 charges. In this case, current is equal, again, to charge per second.
So in terms of current and charge per second, and once again, we're talking about electrons which carry those negative charge, and we're talking about a certain amount of electrons moving at a certain amount, a certain rate to give us that ampere, so many amps. And really, when we think about current flow, we're going to be thinking about intensity that I measured in amperes. All right, so we covered some electronics. We covered some basic electronics in terms of basic electricity, I should say. Atoms, the makeup, conductor, insulator. Talked about semiconductor briefly. We got into a little bit of the mathematics, scientific notation, engineering notation, prefixes, and a little bit of math moving back and forth. We talked about the variables and proportions, direct proportion, inversely proportional. And so all of that will come into play as we continue to move forward. And everything that we've talked about tonight, don't feel like you got to memorize anything. We're going to continue to discuss and continue to build on, and we're going to use, like for example, the prefixes in engineering notation. Use those so frequently that you're going to be in good shape. It's going to be second nature. So we're at looks like about almost 12 to the hour. We're going to go ahead and take our second break. And like I said, the way I typically do is this second break. If you don't have any questions, then you'll break and be done. If you got any questions, I'll hang around. This gives me an opportunity to kind of hang around. And if anybody has any questions that you want to ask, I'm here for you. So if anyone has any questions, I'll open the floor up. Otherwise, I look forward to seeing you all on Wednesday. If you haven't had a chance to try to access the course yet, please do that and email me if you have any problems. Otherwise, I'll see you all on Wednesday. If you have any questions, like I said, just hang around and feel free to speak up. Otherwise, y'all have a great night. We'll see you Wednesday.
Thank you. You too.
Absolutely. Yeah. Look forward to having you guys in class.
I got one quick question for you, Mike.
Absolutely.
When we go back and look at the material, is it just going to be in the video form, or is it going to be, where we can go back and look at it as you looked at it? Like, I guess it